Are we now on air? On air now? Good afternoon to everybody. I will open the second session of my course on radiation effects on microelectronics. Some new slides. Audience spoke to me. Just as a short. Remember, we were worried about cosmic environment. Problem. It is a problem. It is a problem also increasing high altitude airplanes. Sure. And the new for today is the new standard ISO 26263. Now it's compulsory to have error detection and correction systems, any embedded system controlling a civilian vehicle. Why? This thing started, not clear if it was a bit or not, but it started in 2005 and 2007. And it was declared by a jury that the responsible of those accidents, one of them killed one woman, was responsibility of the embedded system controlling the accelerator pedal. Okay? And nowadays, the problem is worse. Nowadays, we want to get level 4 vehicles, so nowadays, one standard for the automotive industry. So single event effects is not academic anymore. It's an everyday. There are similar standards also for servers. As a delay. There is also similar standards for servers. You know, today is the day where everybody is doing Ghibli animations using artificial intelligence. But that artificial intelligence is in server farms everywhere in the world, and they are also sensitive. Benefits is here forever. Today is not due to the conventional electronics, but to other something. Nanometer is huge. Okay, we use 65 nanometers. There is a library, the DARE library, developed by the European Space Agency. So you can make your satellites using that 65 nanometers. But the frontier in analog design today is 28 nanometers. And in digital design, the frontier today is in 2 nanometers, 3 nanometers. Okay? The technology you have in your laptops and in your cellular phones is around between 7 nanometers, 5 nanometers. So single event effects are occurring at every moment, even here down at the ground level, where the amount of the neutron flux is almost ridiculous. Okay, it's almost ridiculous, but the vulnerability of the electronics. So nowadays we have a problem, standards. And I think it's good news for all you nuclear physicists and particle physicists, because we will have jobs in the industry aplenty. Okay, this is the taxonomy of single event effects. Today I will speak about destructive latch-ups, not in power, but in signal electronics. The conventional view is to have recoverable events, digital single event effects, and transients. Transients, in principle, are not a big problem but transients can be captured by the digital electronics and confused with a valid pulse. So at the end, single event transient glitches is also a thing to consider. Okay. Single event effects are not a device effect. They are a system effect. So it's important because up to past Monday, you are nuclear physicists, you are particle physicists. So the amount of electronic design you need was almost basically you needed to know about device physics, that's all. But in the case of single event effects, because it is a system effect, you need to know at least the first steps of electronic design, because without that, it's impossible to analyze the thing. Okay? So this is a digital chip, very old. Typically, we use these digital chips. Those in particular were made in our collaboration. Those are single transistor devices. Those are analog blocks, basically amplifiers, a ring oscillator, and a static random access memory, and a shift register. The problem with bit flips is here. Single transistor devices are just capable of producing single event transients and cumulative effects, damage, PID, and analog blocks can only have single event transients. Those are the analyses. Typically, we show our results in terms of a cross section against the energy that the particle gives to the bulk of the device. LET, linear energy transfer. That's those are the typical figures of merit we use. And these cross sections, in the case of nuclear physics, cross section is important, but at the end you are expecting a few events, okay? Because you have an sparsity of targets. Here you have billions, literally, of targets. So these kind of cross sections are extremely bad news in the case of microelectronics. It's better to have the cross sections here, or even to have no cross section at all. Okay? It's impossible to have no cross section at all, but the take-home message here is we want no cross section, and just in case, the minimum amount of the top level of that cross section, because the number of targets is around 10 to the 8, 10 to the 9. Okay? Let's go to electronics. The first thing to consider is that's the simplest electronic circuit. Basically, it's an inverter. So you put here one, you get 0. The output, if you put 0, you get 1. That's an AND gate. So you need to put 1, 1 to get 1. 1, 0, 0, 1 is 0. 0, 0 is 0. And that's an OR gate. 1, 0, 0, 1 is 1. 0, 0 is 0. 1, 1 is 1. But those are the implementations using electronics. Just for you to see, because I will launch simulations on 6 transistor SRAM. That's a standard in the business. And also, this is the signal we see in an inverter. Okay, it's not magical. It will not go to 1 or to 0. It has a transition time between one voltage level to the next voltage level. The reason we use digital electronics is because we can have a lot of noise here. It will be ignored. Okay, but if the noise is going to that level, they will be identified as a valid one. If the floor noise is beyond one level, it will be identified as a 0. Okay, so those are the location of single event upset sensitive areas in this very simple device. This device is oak. This one, single event transient, single event transient. Which is the concept to analyze from the point of view of electronics. This is the same inverter. Okay, the net effect of the nuclear interaction in the device is the appearance of a pulse extremely fast and extremely high in the milliampere regime, or 10 milliampere current pulse between the drain, and the bulk connection. In that case, the bulk connection of the MOS is ground, but could be any other connection. So every transistor, when you consider the whole level, has an equivalent capacitance at the output. So the point is that you are generating charge. Charge that goes to one electrode or charge that goes to ground. We define the critical charge as the one capable of changing the output. Okay? That's the name of our game. If the charge generated going to one of the electrodes, in particular, in this case to that electrode, the output electrode, if charge is high enough, the amount of charge generated is high enough to change the physical state, we will have a single event transient or a single event, depending if the device is a pure combinational or if it is a pure sequential, okay, or any combination of both. At the end, you will have combination. At the end, you will have automaton, infinite state machines that everywhere. None of you knows about the microprocessor. Some of you know about the microcontroller, but the real master in digital electronics is the finite state machine. It's a non-programmable, sequential plus combinational. Typically, is the finite automaton is the design we implement in a faster. Okay, this is a simple simulation I will show in a moment, where I put 165 nanometer PMOS from this library. That's Acompanhe Korea. And that's MMOS, where I decided to put the impact. Effects. This is the input. There. That's the output. Take into account that it takes some time to go from 0 to 1. It's inverted. Okay? 1, 0, 0, 1. And this is the effect of that. Very simple to make. I will launch a simulation in a moment. It will be available for you if you are interested in launching your own simulation. The program to run those simulations called LTSpice is totally free from analog devices. So you can go to Google, put LTSpice, and then you will have so this is the non-single event effect device to design that device. Designing with transistor, in fact, is very easy because the only parameter you have that is the form factor. Form factor is defined by the large of the transistor and the width of the gate. Okay? So basically, when you are designing this kind of things, you have to know the topology, you have to know the voltages, excitation voltages and the bias voltages, and then you decide which is the amount of current you want to go through this transfer resistor. Because any transistor at the end is a resistor controlled by a take that message in your brain, okay? Very important. Transistor is short version of transfer. So basically, we are controlling a transistor, the resistance from here to there, and we control that resistance using a signal. That's simple. That's the only trick you need to know in electronics. So for you at home, you can launch simulation. Okay. Simulations are prepared to give you the results, and it's working perfectly. You can improve the slew rate here, the trailing edge or the rising edge. It's up to you as a designer, considering the amount of capacitance that you put there. That's all you need. If you go to the single event effect simulation, is no particle here. Particularly, I was considering calculation of calculations. Etc. But this, in particular, was typically an alpha particle. There are formulas. No by hand. By hand. Not elaborated further. But it's not a big deal. And in fact, during the break, I will open one book I want you to have here, because in my opinion, it's one of the best books written in the field. It's 2013, but it comes from NASA, a lot of researchers. I think that you will have everything. In fact, it's the main book I use for. So, again, in this case, go to the run, and magically, there you can see the comparison. Okay? There you have an inverter working perfectly. There you have an inverter where suddenly a glitch happens. A glitch can happen in electronics from almost every electromagnetic, ballistic deficit everywhere, fault in the ground, or a single event. Okay. Let's elaborate. You can also try to understand, in fact, you have to, when you are designing, not at the electrical point of view or the electronic point of view, but at the solid state point of view. Then you will have to use another software. The name of that software is generically known as TCAD. There are companies that will not disclose the name. Anyway, I've been aware of different. So this is a mixed simulation where you are doing a finite element analysis of one of the transistors. Remember, that NOT gate was comprised of one PMOS and one NMOS. This is the NMOS section of the NMOS. You have to draw all the structures. You have to consider all the doping, the geometry, blah, blah, blah. Combine the TCAD simulation with a SPICE simulation, whole circuit, and here you are doing solid state physics, okay? Because you are considering now all the bell and whistles typical from solid state physics of a semiconductor. It's important when you are designing not in the electrical level, in the level of schematics, but when you are in the foundry, okay? In particular, this is very important when you are designing detectors. And this is the book. Yeah, we show the book. SRIM Environment Electronics, Kressler and Mantus, the editors, CRC Press, 2013. In particular, this one came from the chapter one of my. But I recommend you for your studies is that thick. Well, memories. The most used memory today is the dynamic RAM. The dynamic RAM is an electrostatic RAM. Basically, it's an array, huge array of capacitors controlled by a FET gate and also with a regenerative circuit to compensate any leakage in the capacitor. That's the name of the game. Those are parasitics. This is the bit line, and the word line to choose which capacitor you want to write in or you want to read out. Okay? This system in principle is surprisingly very resistant to single event effects. Why? Because you need a huge amount of charge to change the value of the voltage of that capacitor. But they are diminishing, 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 and diminishing. So it will be, we will get to a point where drums will be not useful. We are starting to see, we are starting to manufacture magneto rams. Okay, they're just probably they will be market at a very price with rams the spring of next year. China, they are starting to sell, but in principle, this is the horse of our memories. A solid state memory is an array of billions, this kind of thing. This thing is good for G11. But take home message, take care that the capacitance, this is a charge, CS is going down and down and down. This is the origin of bit static RAMs. Where you can find a static RAM? In a computer, it's the most expensive RAM, is the cache embedded in the microprocessor. Okay? In fact, the total price of a processor when you want to overclock your computer, or you want to upgrade your computer, what you are buying, in fact, is not the microprocessor part, because basically the standard, the arithmetical logical unit and the automaton controller is basically the same, but what you are really buying is more SRAM. That's what you are paying for. What is an SRAM? Basically, it's a feedback of two NOT gates. Okay? So you will have one, that feedback goes to one stable state, and you will have 0 if that feedback goes to a stable state 0. Point is that point in the bit flip is that you will have a feedback. Take into account that from single event transient to single event offset, you need a feedback. Okay? Even for destructive single event offsets, latch-ups, you need a feedback. Okay? In that case, the feedback is at the design level. Again, same. Critical charge, C load, those are the parasitics. C load is the load of the next inverter. So if you have enough charge to change, for example, the state of that output, it will change by feedback. And you have also N1 and N2. They are key transistors that isolate the RAM from the outside. It's important because one of the simplest ways to restore the value of that memory cell is using M1 and M2 in specific times. I will show you in a moment in a simulation. Okay? But things are starting to get complicated. Sorry. Remember, you have millions and millions and millions of systems embedded in a matrix. So this is a simulation. Okay. Again, I designed a very simple and very inefficient. Okay, because I was not interested in it. I designed a 6T RAM using 65 nanometer technology, exactly like the one I showed you in the inverter. It's not very complicated because once you master the design of the inverter, you only have to copy and paste and turn 90 degrees. Then you have the other inverter. The rest of the business is just to make. Here you have one output transistor controlled by the word and one input transistor, or vice versa. And I put the impact here. It's basically the same 1 milliampere. I have a formula for that, but it's important. This is only for the simulation because I'm just using LTSpice to generate signals, changing signals to have some interesting dynamics in the memory. So that's the impact, 1 milliampere here. The negated output was very stable here. Basically, it was 0. But suddenly, you get a single event transient. That's a transient. And the transient is feedback to the other one, this inverter. And then you have a logical state change. So that's a bit flip. That is the bit flip is recovered because I decided to cut connect the RAM to the external inputs just to restore. So basically, we are looking here is a bit flip. Okay? And then from that bit flip, I decided to isolate SRAM. Again, it's not very complicated. I recommend you to use that at home to understand what I'm doing here. I decided to show you real glitches. Those are glitches coming from the electronics, not coming from the impact, because this is the no single event effect memory. So this is the good dynamics, the nominal dynamics of that system. Okay, the system is resistant to glitches up to a point. Has to be. For that reason, we decided some time ago in the industry that this could be the force of static the 60 on a standard. If you open the same pad with a current, have not related to the nominal dynamics, but related. I know you are out of the water with this kind of circuit design. So it's not your typical business. For the reason I made the simulation, just for you to get used and don't be afraid by electronics, okay? Because at the end, we typically made one standard cell like that, and we replicate by billions automatically. So the design ends at this stage. Okay, let us continue. The reason is I'm trying, but I have. Okay. So, as I promised to you, now we will understand from the physics point of view what's happening inside. This is exactly. The key transistors are not important anymore. Okay? And it's not exactly the same one because it's a master-slave details. Doesn't matter. The point is that this is a flip-flop. Any 60 RAM has a flip-flop inside around it. I made a full three-dimensional design of the transistor. That's the view of a real transistor. Okay? And through some calculations that took me 3 months, okay, I decided that that was the real track of a particle. That track is depicted in terms of the amount of charge you are creating along the track. Okay, so the simulation predicts that a bit flip happens when the transistor C4 is hit by a 15 MeV oxygen ion. Okay, this for you basically, because I knew you were asking for about. So this is the simulation. The model took some time to develop. Those are the transients. We are looking at the VA, yeah, and VB, yeah, and the current through the drain. Okay, those are the, but in that case, we can make an experimental verification. In fact, the prediction from the model was that using a critical charge of around 270 femtocoulombs, this thing makes a big difference. At 14 MeV, we have 172 at 15, and that was tested, published a long time ago. I was younger. A long time ago in one of our Radex, okay? Because probably on Friday, I will speak about experiments, and I will show the experiment that tested that precise simulation. Okay, so you have some capability of predicting in which environment your device is hard enough to survive. Back to 2025. Today, this is a FinFET. This is not the typical MOS. FinFETs are only for digital design. They are switches. For sure, they are transfer resistors, but it's not useful to use for amplifying or filters or whatever signal conditioning application you have in mind. Okay? We still are attached to MOS at 28 nanometers, but if you want to make extremely fast computers, then you have to go down and down and down, deeper, deeper. You have a drain, a source. The back gate is not, gates are not in top, but surrounding the main semiconductor. In fact, it's a FET, field effect transistor. Okay, and this structure, I will share with you simulations. That's just for knowing typical IV curves, IV plot. Know if this thing can be used for signal conditioning. It cannot. Saturation zone not horizontal enough. So forget about using. This is in fact a 32 nanometer FinFET. Remember, today we are reaching the 2 nanometer. No, in fact, we use as switches only. There is no saturation zone in the output characteristic. This is for the input, this is for the output, just for you to know how to characterize this kind of device. Okay, that's a more realistic view of the FinFETs, because we don't use one FinFET. We use groups of FinFETs to get enough current. So this is the inverter. Remember, an inverter is the basic building block of any digital design. They don't make good inverters. Remember, a good inverter needs to change from the state from 1 to 0 almost no time. But this takes voltage, take time, but we don't know how to make it. Okay, go to TSMC and you will have a fixed figures salary at any moment. But that's the best we can do at the moment at those scales. Just for comparison, 0 nanometers is the range of atomic physics. And we are just one order of magnitude. Okay, which is the problem? That any FinFET, remember, to have some basic digital building block, we need 2 FinFETs. One NMOS, one PMOS. This is the same inverter made with MOSFETs. This is the PMOS. MOSFET is a cross-section. Okay, this is the cross-section of an inverter. That the PMOS transistor, that the NMOS transistor, but in the middle, the substrate, you also have behaviors like a thyristor or a silicon control. Okay? A silicon control rectifier operates like a couple of bipolar transistors back to back, has a double feedback. This device could be unstable at a snap. In fact, if you go beyond that, the anode to anode, okay, voltage. If you stay below VH, no problem. That device will be there making nothing. Because that's exactly what you want to make to device, parasitic device, okay, nothing. But if for some reason, an impact of a particle, the voltage is unstabilized enough, go there, you have the snapback, and then the device is self-conducting, goes to a stable state, and start to grows and grows and grows and grows the current up to the point of the only thing you can do is to detect the increase of power consumption and to cut the voltage moment. Thing happens microseconds. Okay, yeah, but I can disclose that we have 2 PhD in my department making precisely a circuit that probably we will test to facilities here exactly for that, for detecting voltages, current overconsumption, and to cut for a moment the power. If you go to a FinFET, the thing is even worse. Yeah, because remember, you don't have only one thing, you have several. So at the end, you have a lot of, this is exactly the same, it's an inverter. Okay? But consider an inverter made with FinFETs, several fins. And you have a lot of devices, parasitic devices here, essentially this one, that one, that one, that will go exactly the same, to the thyristor. FinFETs are extremely sensitive, and for that reason, the neutrons at the ground level that were not important 10 years ago now are important. Because the single event in this case is not just a corruption in a memory, but it's the destruction. Next time you drove in your car, thanks a bit about the possibility of because this will be parking ground. Okay, let's go quantitative. This is the full set of in the old times. Nowadays, up here it's more than enough. Okay, chloride 35. You can reach that ion. Okay, so the typical experiment, the name of the game is not detector physics. You know, you need to know some fancy words, okay? Just to get into touch with the industry. This is harsh environment reliability. Don't say nuclear physics. If you go to I don't know, to Volkswagen or whatever, and to say, I'm a nuclear physicist, I know about nuclear, you're out. But if you present yourself, I'm an expert in reliability in harsh environments, and in particular, I have worked in large apps, go inside. It's important, very important. Okay, because at the end, you are doing detector nuclear physics. So the point is not only energy, also range in silicon. In fact, not in silicon, because any chip, any die, is surrounded by a package. So the package gives to you some shielding against these effects. It's important. In space is very important, the design of the packages of the electronic at the chip level, because that's the first barrier, the first shield against environment. And then you do a lot of, that's the LET, the energy that you transfer to the device. And then with all your data, you make a Weibull fit, because the Weibull fit is good for having cross sections. What's the physical meaning of saturation? That you are doing bit flips with any particle you. Okay, that's the only meaning. We are interested in having this threshold to the left, because this is safe zone. Any designer will say to you, I want to live in that LET. From that, you are jailed by the statistics. Probably with can go up to silver. More than enough. So you could make sense nowadays. 10 years ago, no. Because I remember that conversation 10 years ago, and I said to you, more energy, more ions, but today, so that the cross sections, this is a lend from physics, but what the industry will, is interested about failure rate and mean time between. It's reliability. Okay, if you look in electronics books about single event effects, always they are in the reliability. You go to the conferences, it's always about reliability, because that's know about nuclear. That I have the two jackets. I can wear the physics jacket and also the engineer. Okay, but if you want to get a decent salary as an engineer, you need to know their catchy phrase. Okay, so this is typically the thing that you are interested to calculate. That's your final product. This is the same Faccio, Federico, working here. And this is basically the flux of protons, pions, and neutrons in the North Hole at CERN. So you need to, when you go to a facility, you need to need the spectrum, different particles that facility can give to you. I choose this because this is the spectrum at the North Hole, the spectrum of protons, pions, and neutrons coming from the SPS, one of the middle rings, the Lord of the Rings. So, work in particular, radiation tolerated electronics for high energy, radiation with protons, blah, blah, blah. So basically, this is the information you need from the facility. That's your final product, and you get a lot of integrals like that in your Python programs. Not a big deal. For us, as a nuclear, for us as a nuclear physicists, it's not a big problem. The big problem is that you need about electronics. So if you control both, a little amount of nuclear physics and a little amount of microelectronics, will have a full. Typically, this was one of my experiments, very old experiments. Just for you to know how we make an experiment. The pelletron that we have near to my office, that the target, the ALBO. Okay, that was one of the targets we use. And then you need a DAQ and a computer to get the result. It's not very different of any conventional setup for a fixed target experiment, because in fact you have a fixed target. Usefulness. Well, in the old days, you need to launch or run a program capable of giving to you not the spectrum of your facility, but the spectrum in the orbit you are interested in, your satellites. Okay, so this is an example of how to make a calculation of single event effects in orbit, particularly low Earth orbit. Okay, we calculate our product was the cross section. Then we go to SPENBIS. In SPENBIS, we choose some orbit. This is the International Space Station orbit. It's standard to test things. And then have those fancy maps of the radiation levels and blah, blah, blah. And with that, you make a prediction of the number of failures you will see during the lifetime of the device. Standards. From the American Society for Testing and Material to the European Space Component Coordination, the 25100, because you cannot fly in orbit nothing without satisfying those standards. In the Americas, you don't have a particular acceleration. Why? Okay, not my AI is devoted also to things that go boom or go bang to kill people. So it's a different business. Okay, but in Europe, we have the European Space Agency. The European Component Irradiation Facilities are in Billingen. It's a cyclotron, the PIF. The RADEF in Jyväskylä, Finland, and also the high ions facility in Louvain-la-Neuve in Belgium. And that was so the ECF is where the European Component Irradiation Facility is located. It's in Norway, okay, in one of the hubs of the European Space Agency. NASA is not a civilian. Okay, NASA is a military organization, civilian. ESA is totally civilian. That's a huge difference. No, it's important to know. For that reason, when we work at ESA, have been working in particular by for projects, we are more open collaboration with scientists, because we are scientists. We are not military. Okay, so those are the spectrum and the ions you have available. These facilities are extremely saturated because not only European Space Agency is testing there, but also the European automotive companies. So now the small accelerators, in particular the one we have in here, doing routinely this kind of experiments. In particular, not single event effects, because single event effects are more specialized, but TD and DD for regular way. Those were the requirements 20 years ago. But nowadays, this standard is very outdated. So there is no a new standard, okay? There are addenda to the standard. But nowadays, this standard is very outdated. The amount of LET, 80 MeV square centimeter per milligram of ions is really huge. If you shoot an 80 to your circuit, you will fry your circuit. So the point is not to fry your circuit. No, the point is to new single event effect. We are not trying to destroy in the hard way. So basically, this is very outdated, and small accelerators can make out now, like the one you have here, okay? Can make now full certificate. Remember, microelectronics, nowadays we don't use the name microelectronics, we use the name nanoelectronics. Okay? So the lead threshold is good news for you. You have to speak with your customer, because if your device, if this thing happens at 40, you don't need to go beyond. So nowadays, 40, there is a lot of saturation. So a standard is a standard. Change a standard every 10 years, 20 years or so. But one thing is the standard, another thing is the relation with customers, companies. And they are not interested in going to 110, because the device will be destroyed way before. It's a matter of getting a deal with today. Years ago. Okay. I will speak about one of the environments I know. Environment. It is one of the more rich environments in those in terms of damage and in terms of because basically we have photons, heavy ions. We also have heavy ions. Okay, we have different experiments ions, protons and xenon ions. Okay, sorry. Protons and sugar neutrons, because once you go beyond 500 MeV, you will have neutron escalation and even lower energy from Fermi breakup, etc. You are expert in that field. So this is the electromagnetic cascade. that's the nuclear cascade, displacement, dose, and single event. And from that, you can make certifications. That was the way of the, because you are not interested in making detectors. Or you can use electronics to make chip detectors, as we do at CERN. Detectors not for the experiments, detectors for the tunnels, because we literally need thousands and thousands of them. It was extremely expensive to have specifically made detectors at the quality of the detectors we have in the main experiment. In fact, that was a long time ago. The reason I went to CERN was working in microelectronics, and they had the best solution for radiation monitors. In the case of radiation monitors, you need a thing to detect those. You need a thing to detect the displacement, and you need a thing offset counter. I will say to use an anecdote. Anyway, this was publicated a lot. In particular, TAIX came to Spain a long time ago, in Valencia, and then Falcheri. As I resume, in silicon, from the point of view of nuclear, the thing to consider is the amount, is exactly like in ion physics. It's the energy per atomic mass unit. When you are shooting protons, the figure is energy. When you are shooting ions, you need to say the amount of kinetic energy per mass atomic unit. Okay? So less than 1 in silicon is important. Now you are working in other materials, but in silicon, 1 MeV per AMU has no well-defined electron-hole ion track, typically electrons, photons, photon scattering for gamma, photoelectric for X-ray. No, there is no single event effect. The TD is uniform, and the DD, the damage, is also uniform, point defects. If you go beyond 1 MeV per atomic mass unit, then you will have single event effects, non-uniform TD associated to the track. So if you are considering only general dose, that's a mistake when you are shooting ions or you are shooting protons, because the dose can be extremely high along the track, okay? And you will have TD effects without going beyond any uniform TAD limit from the industry. And for sure, DDD, non-uniform associated to track cascade. Discussed on Monday about. And also, if you are over the Coulomb barrier, you have nuclear reactions. If you have neutrons, remember, you will have neutrons everywhere in any nuclear facility. You will have neutrons everywhere at the ground level here also. Typically, one flux of 1 neutron per square centimeter and second. That's a typical flux. Yeah, 1, 1.2, 1.5. It depends. But remember, the neutrons have no limit. They will generate if they can. They will generate if they can, if they are thermalized enough reactions, because huge cross sections. So basically, in the case of at CERN, we have DDD, but even you have one nuclear reaction, that nuclear reaction will happen in the silicon. If it happens in the silicon, the track is totally absorbed in the silicon. So at the end, you will have a huge amount of electron and hole pairs without worrying about the shielding you put in the package, okay? Because you cannot shield neutrons, basically. Just to give you some illustrations about this work we did very beginning, my career. Okay, that is we started at CERN. In fact, I studied at CERN the radiation to electronics task force, because the radiation in the tunnels is so huge that CERN, as the facility, make some development. In particular, the Radmon. Nowadays, that's the Radmon in 2009. And now Radmon is even in space in a CubeSat. So the technology has given some, some kickouts, very interesting. Also, at ENTOF collaboration, from here I went to RD50 at ENTOF. That's the dump at ENTOF. You can put some electronics. That's the plastic lamp. This is a Radmon 2009. In particular, that Radmon was installed in one of the tunnels in the North Hall downside to detect radiation, and this is a Medipix. We'll elaborate about a Medipix. It was one of the first pixel detectors for the public. Okay? Not in the main experiments. It's of the spin-off, if you want, of the CMS and Atlas. So I will give you examples of the events we detected in CENGES and also the ultra radiation environment and fast neutron detection at TENTOF. The problem for where we are interested in that particular task force in that moment was that our air conditioning units were shooting out spontaneously. And the reason is that the embedded controller of the air conditioning were being affected by single event effects. Any air conditioning unit is not in the radiation area, but the amount of the energy of the particle is so high that they cross the concrete, and some of them went into and the air conditioning is critical in the tunnels, not only about temperature, but also about filtering. So that was the origin of our contribution at CERN. Then we went into it. It was strictly a problem related to single event effects. Air conditioning. But you get the picture. Okay, that's the Radmon. I will stop in a couple of minutes. That's the Radmon. You can look for detectors here. There are known detectors because the point of Radmon was we know a lot about single event effects, etc., blah blah blah. How can we make a detector cheap enough to put it in the millions, in the thousands? Okay, so basically we use pin diode, we use RadFETs, and we use Toshiba SRAM. This is a typical box. We protect the electronics, interface to transmit the data, and that's the detection. So if you want to make particle physics in the cheapest possible way, this is particle physics. Okay? But remember, what is the name? It's not particle physics. Reliability, harsh environments. Very important. I will make a break here. Hello? Yeah, yes. So we'll start in seconds. Okay. Yeah, just to show you my recommended bibliography. This is the book we are referring to in the previous session, Extreme Environment Electronics. It's an official book from NASA, edited by John Kressler and Alan Mantuth. It's CRC Press. And it's organized as articles. Collection is in fact a collection of articles. Okay, you can see in every chapter a collection of articles from specialists in the field, 2013. Okay, but basically 85%, 90% of the book is still good to study, and you can have in this book the view of the whole problem. For example, in the introduction, you have history, etc. Chapter 2, extreme environment in NASA planetary exploration. So it's important. This was originated for the Juno mission. The Juno is an orbiter around Jupiter. It's now orbiting around Jupiter, and Jupiter, the Van Allen belts in Jupiter are extremely populated with radiation. So, overview, etc. Role of extreme environment electronics in NASA aeronautics, nowadays in automotive industry. Technology options for extreme environment electronics. You also have some physics. Sorry for the delay. Okay, physics of temperature, role in current transport, radiation transport physics. So if you are fluent in physics, you can connect with this book in the first chapters. It's very, very easy for us. And chapter 9 starts with interaction of radiation with semiconductor devices. That's exactly the origin of this particular course on past month. Okay? I think it's a book you need to have in your library for sure. Is one of the most visited by my students chapter. Okay, so for that reason, it's overmarked with a marker. Okay, then you have environment and prediction tools, the orbital radiation environment. Some software CREM is outdated, but it's now we prefer to use SPEMBIS. Monte Carlo simulation of radiation effects is also the name of GM4. You are aware of GM4. GM4 is useful to know where radiation is going to. In particular, I will show you, at CERN we use GM4 for detectors and FLUKA for the environment. Why? Basically because FLUKA is certified by CERN and was developed there. You also have extreme environment in energy production and utilization, extreme environment in transportation. Remember, this book has 10 years, more than 10 years, but we were predicting effects in automotive industry 10 years ago. Chapter number 5, semiconductor devices. Section 4. Chapter 15 is radiation effects in silicon complementary metal oxide platforms. So some of the illustrations in my courses came from there. Chapter 16 is wide temperature of CMOS platforms. Then they went into radio frequency in silicon on insulator. This was high-tech 10 years ago. Now it's standard tech in radio frequency. Silicon germanium high-speed platforms. Again, I remember that we discussed in particular yesterday during dinner about silicon germanium, about the dinner. Also, remember, because IHP is specialized precisely in silicon germanium technologies for radio frequency. I'm making the publicity of this book. I guarantee you that I'm receiving no funds from the publicity of this book, but that's the book I use every day. Okay, then you have silicon carbide. Silicon carbide 10 years ago was extremely high tech. Nowadays it's a standard in the power electronics. If you go into the electronics of any car, in the driving or in the driver of any electric car, you will have silicon carbide everywhere. Passive elements, because passive elements are also important. A passive element is a capacitor, an inductance, or a resistor. They can also fail under radiation. Power-based platforms. Nitride. Nitride is not used at the moment. Photonic devices, extremely affected by radiation. Okay. Radiation hardening by process is exactly what we did in RD50, the RD50 collaboration when we were developing along 20 years. The detectors nowadays we're installing, for example, in experiment, the compound moons. Okay, modeling. It appears also TCAD, or the advanced transistor, mixed mode TCAD tools. Remember, mixed mode, you have been looking at the two mixed mode TCAD simulations, where we combine the SPICE, the electronics, plus the solid state physics in one small device. Etc., etc., etc. Even the qualification methodology for extreme environment electronics, where you have the description of the standards and how the engineering refer to this engineering reliability, how they call us from their view. Okay, so I think that the jargon is important to be understood by them. And then from the chapter 47 and beyond, you have specific designs made resistant to. So if you want to have a crash course on electronic design, this is again the book follow, because they are small articles, so you don't need to read hundreds of books to master, but specifically the problem you are interested in. We'll stop. The book is up to you. So I will continue with the course. Okay. Remember, before the coffee break, we were trying to use to take advantage of the results I showed in conventional electronics to make an extremely cheap detectors. Detectors of the radiation environment in the tunnels at CERN. Okay? So they decided, the task force decided to use RadFETs. RadFETs are made in an Irish company, Tyndall, an Irish institute. Nowadays it's a company. I will not disclose the name of the company. Okay, Google it. But basically it's an institute in Ireland, Tyndall, that are responsible of making RadFETs. RadFETs are sold by thousands and thousands at every hospital. Okay, so any nuclear worker, and the people working in radiology are nuclear workers, have that qualification, use RadFETs. In principle, a RadFET is just looking at the threshold variation of the PMOS transistor due to radiation. So it's the bread and butter of TD, but nowadays used as a detector. Okay. In the case of neutrons, there are several possibilities, but one of the cheapest is to know or to look at the dark current coming from a silicon P intrinsic N diode. This is a Siemens BPW34 because it was chosen, Thijs told me a lot of years ago, because basically it's a big area pin diode. That's all. And for the single event upsets, well, why not to use a static RAM? The static RAM is totally sensitive to single event upsets, so it's a basic counter of impacts. Remember, a SRAM has the structure of a matrix, so it's perfect. and it's dirty cheap. Okay, so basically you put a lot of zeros in the memory, and then you read the memory. If you are looking at ones in the memory, okay, you have bit flips, and you count the number of ones. It's as simple as that and very useful. Probably on sexta-feira, on Friday, I will speak about one of our experiments we did in Sevilla using the neutron beam in Sevilla, using exactly the same trick, but that time in an FPGA. Okay. So anyway, you can go to the LHC radiation monitoring system Radmon, proceeding of science, etc., to look at this technology. Okay, let's go into the solid state physics. For the TD, that's a MOSFET, in particular a P MOSFET. Okay, as you are aware, we generate in the silicon dioxide a lot of with free electrons, so we will have electrons and holes. The electrons will leakage in milliseconds, but the holes tend to stay in the oxide. The holes will generate, sure, an electric field, and that electric field goes against the electric field you need to generate in the channel of the device. So you will need more voltage to form the channel when the device is heavily irradiated. It's that simple. So you basically test the amount of dose, amount of energy given to the oxide, just by looking at what voltage your device is going on or going off. That's all. Very simple. So those are the calibration plots. And even you can go, this web was working 1 year ago, I don't know nowadays, but anyway, you can go to the Radiation to Electronic Task Force where you have plenty of information of this technology nowadays. This in particular is used for Atlas, for the tunnel in Atlas. Displacement damage measurements with pin diodes. You have two techniques. One is the forward. Okay, in the case of forward, it's exactly the same. We look at the threshold voltage in direct bias to get current flowing through the device. With Rico Rabotti, BPW34, the Siemens, etc. It's a commercial silicon pin diode. Look at the fluencies, 10 to the 12, 10 to the 15 neutrons by square. It starts, this CMRP, not the BPW, this was made specific for dosimetry, for the displacement damage symmetry in one university in Australia, Wollongong, that has a whole set of technologies for dosimetry. So if you want to learn dosimetry in electronics, I recommend you a short stay there in Wollongong. And also the other procedure to use is to look at the dark current. You bias the opposite way the diode, the pin diode, and you look into the dark current of that diode, because that's another procedure. I prefer by far the dark current because it's even simpler to measure. It's operational. Gregor Kramberger was one of the main developers. Now Gregor Kramberger is the spokesperson of the DR3 collaboration. So basically what you are looking at is at the beginning of the radiation hardening the studies at CERN that they went into detectors, and nowadays is going into detectors, electronics, and whatever, not from the point of radiation environment in the tunnels, but from the point of view pure detection of particles in the big experiments. So basically, we started here. For neutrons, wait, you have here the IPEN nuclear reactor, okay, because you asked to me about how to generate one MEV. We generate in the trigger reactor in Ljubljana, and basically in the port, we put a cadmium filter, and from the output, you get 1 MeV. Typically, in a nuclear reactor, you have between 2.2 up to 3 MeV, more or less. You filter out any other neutron. At the output port from the cadmium filter, you have 1 MeV. That's the standard. It's important for displacement damage, don't go beyond the 4 MeV in silicon, because the cross-section for the first nuclear reaction in silicon, silicon to magnesium plus proton, yes, is at 4 MeV. The next reaction is aluminum plus alpha at 6 MeV. So if you are shooting 14 MeVs to a silicon, you will have plenty of nuclear reactions. But if you are interested only in displacement damage, the first figure of merit, then you need to go to 1 MeV in silicon, because there are no nuclear reactions at 1 MeV in silicon. Okay, in other materials it's different, but in silicon the threshold is 4 MeV. It's important also to know about thermal neutron. When you are in an environment rich in water, any wall is rich in water, because concrete has water in the composition. Okay, your neutrons will become thermalized. When you thermalize neutrons, they will generate nuclear reactions everywhere. So it's also important, because this Radmond is for protection, it's for dosimetry, it's for protection of equipment and people. Okay, it's also extremely important to know about thermal neutron damage. And thermal neutron damage is typically detected with boron. Boron has the huge, the biggest cross section for capturing a thermal neutron. Where you do have boron? Basically in a B-dope based, in a bipolar transistor. It's for free. You buy the bipolar transistor, then you have boron. Okay? So that trick was used looking at the power, the current consumption in the base of that bipolar transistor, because the variation in the base is informing to you about how boron has not been destroyed by the thermal neutrons. Okay, if you destroy the boron because you transform into lithium and alpha particles, then you will have a diminishing the doping base in the boron, and the bipolar transistor will start to go astray. So if you want boron for free, go to any bipolar transistor and put in front of a thermal neutron. It's good to know. This was presented by Igor Mandik, also from Ljubljana, 10 years ago, more than 10 years ago, almost 20 years ago, and you can read in the Transactions on Nuclear Science at IEEE, I3E. Hadron monitoring by single event upset counting in static RAMs. With SRAMs, it's not only important to know about the single event upset count, know how many single event upsets you have. So you have an indirect measurement of the flux of ionizing particle you have. But also it's important because you can have almost for free some single event upset classification, some looking at the different sensitivities as a function of the biasing voltage and the cross section, you know, because you have calibrated the device before. This is the calibration of the device, but this is a standard and very outdated, very big SRAM. It's still, it is not in production, but the stockage is huge, and we typically go for this kind of SRAMs. In particular, for cheap single event upsets detectors, we use this Toshiba. That Toshibas are now in orbit. And one of our satellites from the University of Sevilla, and the payload was this memory, because it's extremely cheap and extremely effective and very well calibrated by SEMS 20 years ago. This is just the byte error counting as a function of power supply. From that, you have some classifications of the kind of particles hitting your memory. Okay, so let's go to radiation environments, two of them. Atlas was, the experiment Atlas was one of the main developers of Radmond. MS went into the wagon, jumped into the wagon years later, but we are using exactly the same technology. And one of the most interesting, in my opinion, experiments made at CERN, the CERN neutrino to Gran Sasso experiment. I think that you here remember that the neutrino faster than light in 2011 was a mistake, okay, from CENGES. Because at CENGES, we generated neutrons in the hardest way, just by shooting by a proton beam from the SPS, high GeV proton beam. We focus with a horn in helium bags and a reflector. We focus then and avoid the jets. So at the end, you have a more or less oriented pion and count beam. That pion and count beam crashes into the wall in the tunnels. Then you have muons and neutrinos. The muons will be lost in the ground, okay? But the neutrinos, the idea was to detect those neutrinos going underground up to Rome, from Geneva to Rome. And there they have a lot of detectors, photographic layers detectors, okay? We were interested in that experiment in know about the flavor changing of neutrinos. And in fact, we detected not faster than light the neutrinos, but tau neutrinos. It was important. Atlas, to know about, it's exactly the same in CMS. I will give a colloquium about CMS, so it's fair to have also some words to Atlas. Okay, so the thing in Atlas is not to protect the main detector, but all the ancillary systems we have around Atlas, and in particular, the mainframes we have in Atlas and in CMS in the first floor from the ground, okay? Because the radiation can cross through the concrete walls and reach the servers. So that thing I told you about is important nowadays for artificial intelligence to protect the servers against single event effects. Is the bread and butter of every day at CERN in the second level trigger. In the second level trigger, no, in the first level trigger. FPGAs. I don't know what Atlas have, but I know for sure what CMS has. Basically the same technology. Okay? So this is the environment in Atlas. You have total ionization, those 100 kilograms. This is the experiment, okay? Thermal neutrons, such radiation levels cause damage to detectors and readout electronics, not only in the detector, but in the surroundings. This simulation was made with FLUKA, and it's for 1 MeV equivalent neutrons. Just to know, the radiation is not 1 MeV, for sure, but FLUKA transforms into 1 MeV equivalent just to calibrate with the plots you have for studying the electronics and whatever. This is the CENGES, no protons due to target area shielding, no pions, but for sure we have muons, a lot of, stray gamma rays, slow neutrons, and fast neutron from the beam target spallation. CENGES was a very dirty experiment in terms of parasitic radiation. That's for you to have an idea of the amount of dose for our electronics and why at CENGES the air conditioning units, the filtering units, in fact, we are affected by single event effects. Because at every pulse of protons going to the target, we generate huge amounts of flash. Even with shielding, okay? Even shielding, take into account that if the energy of the particles flying away is huge enough, a shielding is a target. So it will generate another splash of particles. And that's the end of environment. Just to know you about different environments where Ramon is installed. neutron dyno flight is an experiment where we generate neutrons from the impacting a target, a fixed target. Protons from the proton synchrotron, not from the super proton synchrotron. Okay, it's up to 24 GeV energy. That flux of neutrons is more or less channeled by a steel tube of 185 meters, so we can make a time of flight, and we can select neutrons by the amount of time flying in the tube. That's an area where you can work in. That's the dump, and this is just a cross-section of the measuring station, a cross-section of the tube, and the escape lane is exactly that point. Okay, that's the end of damp rad environment. Basically, the neutron fluence is huge, even in the damp, and the energy spectrum is huge again. Basically, you have no, in the damp, basically you have no thermal neutrons, but without thermal neutrons. Thermal neutrons are filtered out at end off, so you don't have thermal neutrons, but you have everything in the middle. The middle are up to GeV of neutron. Okay. We took measurements using the Radmons, but we were interested in classifying those, which kind of radiation we were in those environments. It was very simple to detect them with Radmon. The alarms went off almost every day. Okay, so the next step, I sent one of my students one summer there, was to use the, back then, brand new Medipixis detectors. In fact, was Medipix 2, because it was the result of a PhD work of, nowadays he's a senior electronic designer in the electronics building Bâtiment at CERN. The Bâtiment 14 at CERN. So Medipix was developed as a high-resolution X-ray detector. Nowadays, it's a particle counter. Okay, it was developed at CERN in collaboration with a lot of universities and research institutes. Nowadays, there is a Medipix collaboration. Whatever PIX nowadays, because this thing has been evolved in the 15 years. And at that time, TimePix was being developed as a particle detector. So this is a spin-off of the PSI-46 and the equivalent chip at the Atlas. PSI-46 is the readout in CMS. Okay, basically it's the same technology that nowadays CERN is selling outside for medical purposes, for space or whatever. It's a huge business at the moment. One question? In the outside. The first question I have to make is which kind of radiation. The second is which kind of device. The third is sometimes annealing can improve a bit and you can recover the functioning of your device a bit. On Monday, we were discussing specifically about the consequences of detrimental annealing. If you are annealing total ionization those, so to speak, holes in an oxide, annealing is positive, okay, because you can evacuate the holes. In fact, that's exactly what we are doing using the tunneling effect in flash memories. In flash memories, we register basically an amount of holes in an oxide, and we tunnel out those holes just for writing again in the. So for TD, annealing would have a positive effect. In the case of a bit positive effect, because I'm speaking only about holes trapped in oxides. In the case of traps in the interface, annealing is totally detrimental. Okay, and if you are speaking about radiation damage, annealing worsens your problem. Why? Because in the case of displacement damage, the damage at the beginning is in the bulk of the device, but because of annealing, it will diffuse. Those defects and vacancies will diffuse in the device, and that diffusion will stop in the boundaries, the surface. And remember, in the case of most electronics, everything, all the interesting dynamic in one surface, a surface near to the silicon dioxide interface. So don't trust a lot into in annealing. My take-home message is annealing always is a double-edged sword, always. Don't trust annealing in any moment. It's better to have redundancy in the device. It's better to have radiation hardening by design, and if not, just to make a substitution of the device. Redundancy the hard way. So, okay, you're welcome. So this is the view of Medipix. Medipix is an hybrid detector, so you will have a readout chip in the back and a detector on top. Okay. We install Medipix 2 in the Cenjes tunnels because the point was to classify. So we were doing, in a very humble way, particle physics. We are not just raising alarms because we were detecting radiation effects, but the purpose there was to classify which kind of radiation we were shooting at in the tunnels. Medipix now is in the 65 nanometers. Okay, you can use Medipix as a cheap calorimeter. Okay, and if you are interested in neutrons, you can put filtering, conversion layers on top, aluminum, thick aluminum, lithium fluoride, polyethylene plus aluminum. The cross sections of each, that's nuclear physics, for sure. The cross section for those materials is different for the energies of different neutrons. So basically, we are trying to turn Medipix into a neutron detector. In fact, it was a neutron detector. Okay, at Radmond, and several years later, in the TimePix at Tentov, was Medipix in those years, 2010, 29, and TimePix 2011, 13, and 14. Okay, TimePix is a brand new. Was in those moments a totally brand new detector. That's Medipix. Okay, so you have an electronics chip. That's the readout. Tomorrow in the CMS, I will speak a lot about readout chips. Okay. On top, you have band bonding. Those balls around 25 micrometers or so. This is the band bonding. In this case, takes almost 1/3 of the total cost of the chip, because you have to solder at that scale. And on top, you have the easiest part. The detector is just a pin layer, and you have the segmentation through the connection to different blocks in the readout. So any readout chip is basically a matrix of signal conditioning elements plus the digital blocks needed to make the readout of the signals captures in every pixel. But when we speak about pixels, we are not speaking about the detector, we are speaking about the chip. Okay? Because the pixelization comes not from the detector, but from the chip. Very important. So there you have a view of how any hybrid detector, that's the name of the game. You have the photoionization, electrons, holes, 3.6 electron volts per pair, blah, blah, blah. From there you have a pulse. You can call this a single event effect. It is a single event effect, okay? But we prefer in this area to call it detection. That current will go through the solder bump to the pixel readout, and it will be, the signals will be processed by the electronic chip. Be aware that in the silicon diode, it is a detection, but in the chip, it is a single event offset. It's exactly the same effect. The name is changing. because that same particle can generate a false bit flip in the registers of the chip. So when you design a readout chip, you have to take into consideration also single event offset from the very beginning, okay? Because it's basically what you are detecting. It's not complicated. Nowadays, to make a Medipix is almost a master degree work or master degree project at any engineering university. It's very simple technology. I will go into details in a moment. Okay, electronics. You know that I like a lot of electronics. Detector, amplifier, charge sensitive amplifier, comparator, the counter. This is the electronics made in the pixel. You will make exactly the same process here, there in the whole matrix. This is the layout from the top. That green octagon is the shadow of the bump where you bond with the diode, okay? That's the amplifier. Look at the scale. It's huge for the today's standard, 55 micrometers by 55 micrometers. This is the preamp, this one. Those are the comparators. Here, this is the disk logic there, and this is the configuration register. 13 bits, where you register the data coming from the impact. And you repeat in the matrix. Okay? So just for you, that you can see that's the beginning of the. But I think that you as particle and nuclear physicists need to be aware of technology. This is old technology. Okay? This was taken from the camera technology in 15 years ago. So nowadays, I think that for your education as a physicist, you need to know at least how this is working at this level. Because if not, you are totally lost. Okay, you don't know if you are detecting something, or if it's a single event effect, or just a glitch, a malfunction, or whatever. From the cartoon, remember, at every pixel, we have a 14-bit register. From the columns, you send the chief register, 256 register. You have a low voltage differential signal input to control the things, and an input-output logic. 32-bit CMOS output, where you read the numbers coming from the matrix, and then you organize everything from the Medipix to the processor to generate the things I will show in a moment. So this is a crash course on particle physics, instrumentation, plus DAQ, plus analysis. Everything in a couple of slides. This was the next generation. Now it's a standard. It's the time peaks, where you can have not only counting, not only PHA spectrography, pulse height analysis, but also time over threshold. Time over threshold is direct information of the amount of energy, the LET, energy given by the particle to the silicon. So remember, LET in this field means calorimetry. What we have in time peaks is more logic. Okay, this is a time peak synchronization logic. Basically, a lot of chronographs to know when the particle hits and when all the charge is collected. That is the name of this time over threshold. Okay, basically how the signal is lasting. This is particle physics. You can have counting, the number of times the pixel detects a signal over a threshold. With the SRAM memory from Toshiba, we were doing exactly that, counting. If you have time over threshold, the number of clock cycles, the signal is over the threshold, then you have a measurement of the energy, the LET, a direct measurement of the LET, the energy transferred to the detector. And if you have time of arrival, then you have timing. Every observable in a pixel in the tracker, in Atlas or our CMS, is actually in this chip. We make it faster, we make it better, we make it denser, but basically everything was from the very beginning time peaks. And there you have the start of analysis. What is doing at the end time peaks or MEDI peaks? Showing you images of radiation, which is the image associated to an X-ray, which is the image associated to a pion, to an alpha particle, etc., etc. In the case of an electron, you know the mass of an electron is 511 kilo electron volts by square centimeter. That's a mass. So that particle, that electron, is easily scattered in the silicon. So it's very simple to identify electron tracks because they are doing, okay? If you look at a lot of zigzags, you are identifying as electrons. Alpha particles. Alpha particles are able to generate a lot of ionization in a very small space because the LET is the energy given to the light is increased with the mass of the particle, with the using in the previous session. So basically, an alpha particle in MEDI peaks is a blob. Okay? X-rays can have energies enough to excite only 1 pixel. But as X-rays are not focused, you have a lot of scattered points, individual pixels in your image. In the case of a proton, very simple to identify if you are lucky enough, because the protons give the biggest amount of energy when they are going slower. And at the end of the running, at the end of the run, the proton will give to the lattice the biggest amount of energy. The name of the game is the black peak. A black peak is very simple to identify here because the proton come into the silicon, and this blob at the end is the signature of a black peak. So if you identify this kind of plots, then you have identified a proton giving the whole energy into the silicon. Pion. Very difficult to locate the pions in a conventional environment. At Cenjes, very simple, okay, because we have thousands of pions, millions of pions, because the pion decay during the flight, and there you have a decay, okay? The pion is disintegrating in front of you. You can look at this in real time, because you are looking at images every couple of seconds coming. We were looking at images from every couple of seconds from the Cenjes. We were in a comfortable room, but this was a decay of a pion. And in the case of muons, a lot of muons, you have a very well-defined track, because for the muon, basically, the silicon is transparent. They give energy in a track, and sometimes you have delta electrons. Delta electrons are very well known in the textbooks, but there you have a delta electron. Okay? So that's an electron scattered by the muon, and those are electrons scattering by who knows what. Yeah, it's, in the parlance of particle physics, is a transverse lost energy, something forever. Because silicon, a muon from the atmosphere can cross 700 meters of rock. So basically, a 300 microns of silicon, in that case, the detector was not in front of the muon beam, muon coming from the experiment, but that way. Giga electron volts. Anyway, so but the muon the proton is big, the electron is too feeble in terms of mass. Muons is in between 200 MeV by square centimeters. So they have the best of the worlds. You can have well-defined tracks. You are looking at here in the silicon of secondary electrons and whatever. Protons, you have to be lucky enough to see the Bragg peak. Okay, those are real captures we made in that summer. There you have a fast neutron. Why do we know we have a fast neutron? Because basically we capture a proton recoil track. Why we do now that this is a proton? Because of the Bragg peak. That blob at the end is the signature of a Bragg peak. This is a nuclear reaction in silicon. Why we know it's a nuclear reaction? Because the amount of ionization is spread in several pixels, and basically we were shooting no alphas. So this is the signature of, we were looking at in real time a nuclear reaction. And this is a muon. This is a cosmic muon because that medipix was in the tunnels in this position, not in that position, in this position. So basically the muon crosses the whole silicon without noticing. A few MeV. In particular, this one, because this is a proton generated in one of the conversion layers in the polyethylene. This could be 2 MeV, 3 MeV, not beyond that. Remember that we were interested in neutrons. We discovered a lot of things, okay? But we were interested in neutrons, thermal and fast neutrons, and we put several layers to distinguish between them. So the main source of protons came from our layers, in particular from the polyethylene layers. More analysis, okay? We are detecting particles, the cheapest way. So for our radiation analysis, because we were interested in nuclear reactions in the silicon detector, okay, we calculated silicon plus gamma and non-elastic reaction. Silicon to 9 silicon, you can make a transmutation, okay, from a neutron to a proton, from a neutron to a proton, okay. So basically you have a gamma, you have a silicon. It's a first reaction. You have magnesium plus alpha, aluminum plus proton, etc. Sorry, you get a promotion neutron, a neutron capture. 29. Then you have the different cross sections for the different reactions, fast neutrons. This is exactly the same for boron, for thermal neutrons, where you have a neutron alpha plus lithium. We detect typically the alpha. So that's the cross section for boron. And this is particle identification by image analysis. Using MATLAB, today we use Python, but this is exactly the same because that's the original image. We locate clusters, we locate tracks, we locate zigzag patterns, etc. So basically we were doing particle physics during a long summer in 2009. It was very funny. It was a project we did and was our starting point, particle physics at CERN, basically. We were doing particle physics from the very beginning. This was the same experiment, but in that case made not at the THENGES, but in the neutron dump of NTOF. And it's up to you to identify things in the image, because you are looking directly at particle images. This is the thing most similar to seeing particles, okay? So basically you have X-rays, try to locate X-rays, photons, electrons, alphas, protons, and minimum ionizing particle. Who knows what is a minimum ionizing particle? It's a catchy name to put, it's able to put, I don't know what it is, but the track is very clearly depicted. So in that case, we detected 9 fast neutrons in 500 events. Okay, and you make your analysis, etc., etc. If you make this the big way, then you are doing Atlas, you are doing CMS, ALICE, or LHCb. But you can do it nowadays with a small detector in your hand. Again, we need to know, remember, we need to know the spectrum. This is always the same when you are looking. We are using the spectrum for single event effects. The name is the same. Now we don't call it single event effects. We call it particle detection. But the process is the same. You need to know the spectrum, and you need to know several windows for scanning in time. Remember, in the case of NTOF, we knew, looking at the time of arrival of the neutrons in one auxiliary detector, the energy of the neutrons coming to the detector. That's the name of the game, neutron time of flight. Okay, basically we generate neutrons and they separate by themselves in a running path along the empty tube, the vacuum tube. So if you make time peaks, if you know the timestamp, the timing of your detection, then you can classify the original event. This in the particle physics is named locating the vertices. So this is locating the vertices in a humble way. And I'm open to questions before starting another part of the session, because I think you will have a lot of questions. If not, I'm making a big failure. That's the end of this session. I will speak about another session on TCAD in a moment, but I'm open to questions from the audience, local audience, or the audience online. Those are educated protons, very well-mannered protons. Yeah, sorry. Obrigado. I strongly recommend for you, if you are not fluent in electronics, to do the homework. I can give to you by email or whatever, or by sharing the link, the simulations. Okay, just for you to get a taste of what is a transistor, what is a structure, etc. Just a taste, because you need to know the language to speak with the designers. Take into account that depending on your career, you can start, I started as a theoretical physicist, then I went into nuclear physics, I continued to microelectronics, then to detectors, and nowadays I'm doing palestras here in the US. So you know how your career starts, but you don't know how your career will continue. So I think it's important to get a taste and the language of the people surrounding you. In particular, if you are doing experimental nuclear physics, or if you are, or you will do experimental particle physics. Okay, and also it's very important when, okay, I will be the designer, and the first thing I will need to know is which are your specifications, and typically your face is, what's the meaning of specification? Without specifications, without translating your nuclear whatever desires and your whatever desires into a technology, I need a specification. How many electrons we will have to capture, which is the time of the event, is the amplification factor you need, the electromagnetic interference, because we will have magnets and whatever. Those are the specifications for me as a designer. In the case, remember, I was a theoretical physicist. I understand your language when you speak about Lagrangians and Higgses and whatever. But you need to make the effort to translate your desires into specifications. If not, it's impossible for me to go to the computer and design for you a readout or whatever. Or you in the future, when you typically you are exactly in that stage, Julie. Because one day you discover that your technology is shared by nobody. You are the only one in the world doing experiments with that technology. So you are the top dog of that technology, and you need to know what are you doing. Because if not, you have a lot of false alarms, false detections, noise, and whatever. Probably you will become designers. the future. I one example of that. Okay, more questions? We are going to questions, Gilberto, from the... Okay. I prefer to... La palestra es muy aburrida para mí y sobre todo es muy inútil para vosotros. Claro, no sois estudiantes de grado, sois profesionales. Y sois profesionales que necesitáis respuestas. You need answers to your problems. So I think you need to ask questions. There is no a silly question in terms of detectors and microelectronics. You need to ask, okay? Take into account that I'm not an engineer. I'm an engineer, but I can understand you because I was a theoretical and I are experimental physics. So I'm in your side of the road, but I need you to speak the language of the other side of the road. So, questions?
Minha pergunta, na verdade, é a questão do MedPix. Você descreveu várias partículas, inclusive também raio-x. Eu queria saber se dá para diferenciar raio-x com raios gama. Ou é o mesmo efeito, a mesma coisa que acontece?
In the case, 2 years ago, we were discussing exactly the same question in Sevilla. When you look at gamma rays with the MediPix, or with any pixel detector, okay? Here. When you have a gamma ray, you will have dots plus quantum electrons. Probably those were secondary electrons generated, I don't know, okay, because we went no further that stage in that particular project. But probably this thing is coming from a gamma, crossing gamma, and those are quantum electrons. That's an electron coming from nowhere, okay? In the case of a lot of gammas, you have dots plus secondary electrons. So it's very easy to identify. One thing is to study the Compton effect book or in a classroom, and another totally different thing is to see the Compton effect in front of your eyes in real time. So I recommend you to do these kind of things because it's the shortest way to understand particle physics by hand. Your fingers. It's a very good question. More questions? Gilberto, from the audience? 15 minutes, I will start the future. Future will be... You are still with me. Don't go away. 15 minutes. Tomorrow. I will not disclose, but I'm just making some marketing about. Important. Okay? So tomorrow at 14 or 16, I guess, 16, we will have a colloquium. Remember, a colloquium, not a conference, a colloquium. So have your questions prepared to discuss about the compact muon solenoid. You know, you start as a theoretical physics, at the end, you finish putting cables in that thing. It's important, it's important. One of the, last week I was in São Luís de Maranhão, in the conference, the spring conference of the Brazilian physicists, physics in particle physics and nuclear physics. And one of the things that I was horrified, okay? I was the first palestrante, the first conference guy opening the conference. I spoke about monolithic detectors and using lasers and proto-microprobes, blah, 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 to classify them, etc. Full instrumentation, no questions at all. Okay? You think that your audience is full of professionals, and they could be, I thought, I'm telling them very simple things. No. The second palestrante, the second guy, was speaking to us, was a theoretical physicist from Portugal, from Aveiro. He was speaking about vector boson stars. And he was totally convinced about the existence of vector boson stars. There are no vector boson stars, okay? That's from the start. And he was speaking 1 hour and a half, almost an hour and a half, about a full fantasy with a lot of questions. This is a mistake, okay? If you go that way, and I don't know, but the full portrait from São Luís was a lot of theoretical physics, a lot of fantasies. If you go that way, physics here in Brazil will never take off. For every theoretician guy at CERN, we have more or less 500 experimentalists. Okay? This is an important number. All our theoretical physicists are in just one building, near to the reception, near to the exit. That's a joke. Okay? The other 500 million physicists, to say a number, are experimental physicists doing experimental physics, screwing things, putting cables, etc., etc., etc. So the take-home message is particle physics is about reality. Okay? They are not flights of fancy. And I will elaborate that tomorrow in the colloquium. Friday. On Friday, okay, on Friday, I will speak about GM4 and SRIM for radiation transport, things, tools of the trade. The solid-state interaction, I will elaborate even more in Sentaurus TCAD, and also about the electronic circuit response, for the case of single event effects. And then it depends, because it's still under working, it's still under work. Depending on your interest, if you are interested in software, I will elaborate 2 hours of software, no problem. But it would be interesting for you because you are experimental physicist, I hope. It's about design of chips, and also about real experiments we did time ago. It was a very important moment because after 5 years of working, the chip is starting to say hello. He said, I'm RD53A. You can program that, and if you got in the image RD53, then you are detecting yourself. Okay? Yeah, but Thomas is a physicist. So Thomas was doing physics from the electromagnetic flavor. Okay? One thing you have to understand is that everyday life is controlled by electromagnetism, not by nuclear physics. Nuclear physics, thanks God, to God, is localized in points. If not, run away. Okay? But the bread and butter of our experimental way of life is electromagnetism. How the magnet is working, how the electromagnetic compatibility is satisfied by my electronics, how sensitive to light is the detector, things like that. So you need to know very well Jackson's book on electromagnetism. For me, it's the best, very hard, okay? But if, yeah, we have suffered Jackson during our careers, our graduate courses, okay? But you need to have one Jackson in your library, because Jackson's is the book you need to know. You can pretend to know nuclear physics. It's not that way. Nuclear physics is just chemistry in another name, okay? I know you are paying my salary, but anyway, it's a joke. But Jackson's is even more important, because every false signal in your experiment is coming from Jackson, it's in Jackson's book, not in Mandel or in any high rank nuclear Bertolucci or whatever. Okay, so I will speak about this, and also, if you have patience enough, I will speak about other experiments I have done during my career, in particular, the design of this kind of electronics and things like that. Okay? Real experiments in my facility. So what do you prefer? 2 hours of software, 2 hours of experiments, mixing of both, it's up to you, because the material is there. I only to put here and there the slides and adding some slides. No asking for the public, from the public? No? Okay, I will do whatever. Thanks for your patience.